Welcome this new class. In the last class we discussed about the linear transformations, and then we have to prove that T of ui is equal to wi. T from v to w is a vector spaces. In this class we discuss about the kernel and range of a linear transformation. Okay, so kernel and range means first we start for the range of a linear transformation. Range of linear transformation, we have a T from u v to w is a linear transformation. That means we have a, this is a vector space v, we have a, this is a vector space, we have a w, and there is a linear transformation T from v to w. Then with the range of this means we have some elements of this maps to the certain like elements of a like this. This is nothing but is equal to, we can say that this is the element of a RT, where this is some of the element of a V is mapped from into this form. This is called as the range of a T. So, range of a T we have to generally denote it as a RT is the subset of all vectors of this W that are image some vector V. We have to taking some vectors V, that is image of this all the elements which is images into a this. So, RT is nothing but is equal to, we can say that simply is equal to RT is equal to T of V, where V is the element of a V. So, we have to take a collection of all the images of a certain element of a V to a in W. That image is make a set, and this set by the elements of a this is the called is a range of a T. And W vector W is the element of a RT. So, we can say like this, we can just say that all the elements which is mapping to this V2 element of this, and this is called is the range of this T. There is means all the elements this. So, there is some exists some V belongs to V, T of W, T of V is equal to W types of element in this. So, this way clearly we can say that all the elements which we have to collecting in the form of this. RT is nothing but is equal to f the element of a T of V, where V is the elements of V. For example, if we take a any linear transformation T from, we have to take a suppose R2 to, we have to define is a R2, and I define the form of a T of xy is the form of x minus y and x plus y. So, RT is nothing but is equal to the element of the type of this. In the RT of this element of a T of V, T of V means T of xy types, and then we have a x and such that xy is the element of a R2, and this T of xy we have to define this form. So, this is the form of this x minus y and x plus y such that x and y is the element of a R. So, RT is nothing but is a collection of all the elements of the form of x minus y. This can be written as in the form of x. We can say that is equal to, if we take a 1 and then we have a 1 and we have to plus y times, we have to just say that minus 1 1, and then the span of the element of this set is nothing but is equal to, you have a 1 1 and then you have a minus 1 and 1. So, this is RT is nothing but is equal to span of this elements of a 1 and 1 1 and minus 1 into 1. So, this way we simply say that the collection of a RT is nothing but is equal to the element of a all the elements of the form of a T image with this thing. Okay, now we have to kernel. Kernel of this means we simply say that if we have a any vector space V and we have a vector space of a W, there is a linear transformation T of a this. Here is a some element, unique element is called is the additive identity of a this. If we have to take a certain element of a this, those element which is mapping to the only to the this 0 map, that is called is the kernel or the null space. We have to just denote it as a KERT or NT, and this is a subset of all the vectors in V that's maps to this vector 0 of this W. So, this means we can simply say that kernel of a T is nothing but is equal to V, which is T of V, which is mapped from 0 of a additive identity of the 0 elements of the vector space W. Kernel of this is the set of all those elements in V that are mapped T onto the 0 vector like this. So, we can say that these are the collection of these vectors, these are the vectors, this we can say that these are the vectors which maps to the 0 vector of this W, and this can be said that the 0 W, and then this set is collection of these set is called the kernel of this T or the null space of this linear transformation. And similarly, the last example we take, I take a R2 to R2 and define the linear transformation in the form of this. We have a x plus y and we have a x minus y, and then if you take a nullity is equal to those elements which map to the 0. So, x y is R2 0 is equal to 0 0, but this is nothing but is equal to x plus y and x minus y, that is equal to 0 0. Then you have a x plus y is equal to 0, x minus y is equal to 0. Then you have to, when you simplify this, you have to get in x is equal to 0 and y is equal to 0 only. So, we can say that the kernel of a T is nothing but is equal to a 0 subspace. So, kernel of a T is nothing but is equal to, we can say that kernel of a T is nothing but is equal to 0 subspace. Then we only the 0 0 0 elements into this kernel. So, only the 0 is the element which map to the 0 to 0. There is no other element which map from T of element to the 0 of this. This is the definition of a kernel of a linear transformation. Okay, now we have two special types of linear transformations. We have now the zero linear transformation, and we have another is a identity transformation. Okay, first we take a 0 transformation. If T is a 0 transformation, and then T is a 0 transformation means we have any element of a T V is equal to always is mapped to the 0 of V. So, all the maps which transform into the 0 of a V. So, this means clearly kernel of a T is equal to whole of V, because this means all the vectors is mapping, because the map is defined is equal to T V is equal to you have a 0 of V. So, this means all the elements is mapping. So, T of V1 is equal to 0 of W, T of 2 to V2, and all maps are mapping to the 0. So, kernel of a T is nothing but is equal to you have a 0 subspace. Now, range of a T means range of a T is nothing but is equal to, you can say that is the similar is a RT is equal to V, for V is the element of this, but V is what? V is nothing but is equal to you have a 0 of V is there. So, this means if we have a 0 RT is equal to 0, then we can clearly we have only the element is this RT is equal to 0. So, when because there is a we have to map define is equal to T of V is equal to 0 of W. So, this means in the image we have all the elements is mapping to the V2 for all V belongs to the V. So, this means we can say that simply these are the element which can be mapped into this form. So, clearly this RT is nothing but is equal to a 0. So, for a 0 linear transformation, we can say the kernel of is nothing but is equal to whole vector space, and range of this is nothing but is equal to the only the 0 subspace for the case of a 0 transformation. Okay, now we move to the next is a we have a identity transformation. Identity transformation means with I of V is equal to V. So, this means we can say that kernel of a T is nothing but is equal to you have a V belongs to the V such that T of identity of a V is equal to you have a 0 of this is nothing but is equal to V belongs to the V, and such that V is equal to 0. So, this is nothing but is equal to you have only the 0 subspace for identity of a operator. So, I of V is equal to 0. So, V is equal to 0 means whole space we have only the in the element of a kernel of a T. In this case, if we have a identity operator, only the we have a 0 subspace is there. Okay, now if we have a RT, if you take a range of a T is nothing but is equal to is the form of a T of a V. V is the element of a V, in place I we have a, and this is nothing but is equal to V such that V is the element of a V. So, this is nothing but is equal to you have a whole vector space is this case. So, we getting range of a T for a identity operator is a whole vector space, and kernel of in this case we have a only the 0 subspace is there. Okay, so now vector space. So, we can just say that these are the very trivially we can say that the kernel and range for the zero linear transformation and the identity linear transformation. Now we have to see one of the an example. Suppose we take a polynomials p2 to p3, then we have to find the what is the range kernel and the range of the this linear transformation. Clearly this is a linear map, and this is because p3, so this means px of the form of a, we can say that this px is the element of a, we have a p3, then that means p of x is the form of a, we have a naught, a1x, a2x square, a3x cube. But what is a t of px is nothing but is equal to p prime x. So this is nothing but is equal to, you have a1, we have a1 plus 2 times of a2x plus 3 times of a3x square. And we know that the kernel is nothing but is equal to kernel of a t is nothing but is equal to, you have a p of x is the element of a p3 such that t of px is equal to 0 polynomial, and then you know that the 0 polynomial is nothing but is equal to 0 plus 0x square 0x cube. So this is nothing but is equal to, we can write in the form of p of x is the element of a p3 such that this is nothing equal to p prime. So this is nothing but is equal to p prime x is equal to 0, and then we can say that this can be written in the form of a p of x is the element of a p3 such that this is equal to, you have we have a a1 plus twice a2 x plus 3a3 x square is equal to 0, and then now we just said that we have a condition is a1 plus twice a2x plus 3a3x square is equal to 0 plus 0 into x plus 0 into x square. This implies that a1 is equal to 0, a2 is equal to 0 and a3 is equal to 0. So this implies that we can say that this is nothing but is equal to, you have a naught, and then such that a naught is the element of a R. So this means we have to just say that kernel of this transformation is nothing but is equal to, you have a constant, we have a element a0 into the this form. Okay, so now we just said into this form, we have to just say that this thing. Now RT is nothing but is equal to, we have a RT is nothing but is the elements of a RT is nothing but is equal to, you know, that is the element of a t of p of x such that p of x is the element of a so you have a such that is the element of a p3, and now in this form tpx is equal to p prime x, this is the element of the form of a p prime x such that px is the element of a p3. We already calculated the p prime x is equal to this thing, so we can write this is the form of a, you have a a1 plus twice a2x plus 3a3 x square. So in the RT we have a element of this types. Now this element can be written in the form of, this can be written in the form of a, we have to just say that a1 you have a 1 and then you have a 0 0 and then we have a take a 2 and so on. Okay, just take this just because it's a polynomials form. So this means this can be written in the form of a, this can be written in the form of a a1 into 1 plus a2 into twice x plus a3 into 3x square. So what this means, this can be written as a linear combination of the elements of a 1 x and x square. So RT is nothing but is equal to span of 1 x and x square. So this way we can calculate the range and the kernel and the rank of this linear transformation. Okay, now we just take a matrix form. If we have a 2 by 2 matrix given by L is equal to, you have a to the power transform. So we try to find we have a 2 by 2 matrix. So we have a A is the form of a, you have a A11, A12, A21, A22, and this is the matrix in the form of a, we have a 2 by 2 matrix form, and then this is L of A is defined in the form of a this A11, A12, A21, A22 ka transpose, and this is nothing but is equal to, can be written as a A11, A of 21, A12, A22. So, kernel of this linear L is nothing but is equal to, I just said that A is the element of a M2 by 2 such that L of A is equal to 0 matrix. So, you can just say that 0, 0, 0, 0, and such that this is can be written in the form of A is the element of a M2 by 2, and this is L of A is nothing but is equal to A11, A21, A12, A22 is equal to 0, 0, 0, 0, and then this is nothing but is equal to, you have a 0, 0, 0, 0 matrix, because A11, 0, A21, 0, A12, 0, and 22, 0. So, all of them is a I j is equal to 0. So, this means kernel is nothing but is equal to kernel of L is nothing but is equal to, you have a simply say that is a 0 matrix there. Okay, so, now this I just say that into this form. So, this is clearly 0. Now, range of a T is the form of a this. So, R T is nothing but is equal to, we can just simply this form of a matrix is the form of a, you have a A11, A21, A12, A22. So, this means we can say that R T is nothing but is equal to is the matrix of this. So, this is we can say into this form we have to clearly this is the R T into this form. Okay, now, we have one more example into this form. So, we have a from now this map we define from R3 to R2. So, we try to find the range and kernel of this. So, first we try to kernel, you that now the kernel is this is equal to kernel of this transformation. We can say that we take a x, y, z is the element of a R3 such that T of x, y, z is equal to R2 0 0 element, and this is nothing but is equal to, you can say that x, y, z is the element of a R3, and this is nothing but is equal to, you have a 0 y is equal to 0 0, and this is nothing but is equal to, because we have to simplify this. So, y is equal to 0. So, we only the fix is the element of a the kernel of a T is the form of a 0 and z such that x and z are the element of a R, and then means we kernel of this T is equal to this, or this can be written as a span of 1 0 0, and then we have to say that 0 0 0 1 is this form by the span of this, or this can be written in the form of this x times is equal to, you have a 1 0 0 plus z times of a 0 0 1, and such that x and z is the element of a R. So, this is the span of these two elements. So, kernel of this T is spanning by these two elements. Okay, now, we try to find the what is the range of this T, and now we know that the R T is nothing but is equal to is the form of a T of V such that V is the element of a R3. So, T of V is equal to this. So, we have a all the elements we check let all the elements of this is the R T is nothing but is equal to, you can say simply is the form of a like this 0 and y such that you can say that this is y is the elements of a R into this form. Okay, so, the kernel of a T we just calculating into this form. Now, we take a R T is equal to into this form, and this means R T can be written in the form of a this is equal to y times 0 1, and then we have such that y is the element of a R, and this is nothing but is equal to, we can say that span of 0 1, this is the element of a R T. So, R T is nothing but is equal to span of a 0 1 we can write into this form. Okay, so, now we have a next example. I have some different type of example I choose. Just we have to try to find the what is the kernel of a this map, We can start with this is our vector space is defined, addition is defined into a this form, and scalar multiplication is defined into a this form, and then map is defined into the this form. T of V1 V2 is equal to 2 times of a V1 and V2. So, we have to try to find the what is the kernel of this linear transformation over the vector space V. We have to V is defined into the this form. Okay, so because V is defined to this form, so this means we have know that the kernel of this T is nothing but is equal to you have a V is the element of a V such that T of V is equal to 0 of the vector space, identity element of this 0. So, first we have to try to what is the identity element of this set, and also we know that 0 into V is equal to 0 by the property of vector space. So, by the property of vector space we know that 0 into 0. So, this means we can put a alpha is, so 0 vector we can find. So, 0 can be written in the form of 0 vector can be written as a 0 into we have a V1 V2, and by the this scalar multiplications is defined of this vector into this form. So, we can say that we can find for this vector space what is the identity element, means what is the additive identity, means whatever the what is the 0 element of this vector space. So, we put alpha is equal to 0 in this scalar multiplication. So, we can just say that we have a 0 into V1 plus 0 minus 1, and then we have a 0 into V2 minus 2 into 0 plus 2, and now because 0 of V1 is equal to you have a 0, and this is equal to 0 plus minus 1 is equal to minus 1, and then you have again 0, and this is again 0, and this plus 2, so this is equal to you have a minus 1 comma 2. So, in this case we can say that for this particular linear transformations we have a additive identity of a V. So, 0 of a V is nothing but is equal to, so 0 of V in this case we have a of the form of a minus 1 comma 2. So, if this minus 1 comma 2, so we try to find the kernel of this means we can say that kernel of a T can be written in the form of a V is the element of a V such that T of V is not 0, but is a 0 element here minus 1 comma 2. Okay, so now we just try to find what is this. Now, map is defined in the form of a 2 times of a V1, V2 and so on. So, we can just write into this form V is the element of a V such that we have a write into this form V into V, then we have to T of V is equal to you have a 2 times of a V1 V2, and that is equal to minus 1 comma 2, and then again by using the definition of we have to using this scalar multiplications. So, we have a 2 times of a V1 V2 is equal to this thing. So, we just write a 2 of V1 we have can write a 2 times of a V1 plus 2 minus 1, and then we have a 2 times of a V2 minus 2 into 2 plus 2, and then we have a minus 1 and 2 is this. Now, this can be written in the form of a V is the element of a V, and now simplify this we have a twice V, and then we have a plus 1, and then we have a this can be written as a twice V minus 2, and this is equal to you have a minus 1 comma 2, and now we have to try to solve this system of equations. We have a twice V plus 1 is equal to minus 1 V1, this is V1 and this is V2. So, twice V2 plus twice V2 minus 2 is equal to you have a 4. So, you have a twice V2 is equal to 2. So, this twice V2 is equal to 4. So, V2 is equal to you have a 2, and then we have to calculate what is a V1. So, twice V1 is equal to you have a minus 2. So, V1 is equal to you have a minus 1, and then we can say that V1 is equal to minus 1 and V2 is equal to you have a minus V2 is equal to, you have a minus 2. So, this means the elements of this is the simplify into this form. You have a 2 comma minus 1 comma 2 types of elements are there. So, this means we can say that this is nothing but is equal to you have a minus 1 comma 2, and this is nothing but is equal to is the 0 of this vector space V. So, in this case we can simply say that this means we can just say that we try if we take some different types of a vector space, and then we have to first in such type of a questions, first we check what is the 0 of our vector space. So, in this case our 0 additive identity in this case. So, additive identity for this case you have to know that this is equal to this minus 1 comma 2 is the additive identity, and if we have to just this 2 V1 plus V2 minus this. So, V1 is equal to minus 1, and then we have a V2 is equal to we have a 2. So, this again we have to getting the identity of this, the kernel of this T. So, we can say that kernel of a T is nothing but is equal to we have a identity of this identity vector space or identity 0 subspace of this particular vector space V. Okay, now I just take so many various types of examples, and this for how to we calculate the range and kernel of this given linear transformation, because we have to discuss some more results. With the help of this result we can easily calculate the kernel and the range of any given linear transformation. So, I just stop today lecture here, and we continue in the next class some properties of a range and kernel, which is very useful for solving the problems and some applications also. So, thank you very much for this lecture. So, we continue into the next class some basic important properties of a range and kernel of a linear transformation. Okay, thank you very much.